Good afternoon, everyone. Fortunately, I'm not standing between you and the reception. There's at least one other person doing that. I appreciate the opportunity to talk to you about this activity. And just sort of by way of introduction, I've been a data scientist for about 30 years. And about 8 years ago, I went to RPI and was given the opportunity to create an entire curriculum, which I'm going to tell you about. And I'm going to tell you about the consequence of creating that curriculum. And maybe some of the things you've heard earlier you might see show up in this particular presentation. So here's my agenda. I want to do two primary introductory things. And the argument I'm going to make is that any data science or data analytics education or training today is a cyber learning activity. By definition, the concepts, the tools, the interaction are fundamentally being conducted in an electronic world. And that doesn't matter if it's face-to-face or if it's asynchronously or online or whatever it is. So I want to go back and show you something about cyber learning because I think it's going to become important. Well, it has been important for me. And then I'm going to, I rarely can give a talk without showing this slide on data, information, and knowledge. And a reminder, we've been doing this for 8 years. So we have data science programs and informatics programs that are being taught for 8 years, not 1 year or 2 years. So we have a lot of assessment and evaluation studies from it. And then as I further unpack, I'm going to tell you a little bit about a metaphorical approach I use to data science in the delivery of the data science, analytics, and related curriculum. That has to do with anatomy and physiology. And then I'm going to talk to you about sediment. And I'm not going to tell you what that is. You're going to have to wait for that. And then I'm going to get to a little bit the university catching up a little bit, but how our fundamental core curriculum in response to data is being changed or has changed. So here we go. This is a figure. Actually, this figure doesn't actually appear in this report, but Christine Borgman from UCLA chaired a very nice committee in 2007, 2008, produced this cyber learning report. And I used this to motivate a lot of things, apart from advancing the slide too quickly, motivate a lot of aspects of how people and computers generally interact in a large number of settings, in research settings, in education settings, and just generally in collaboration. So I want to just take a minute or so to go over it. First of all, there are 5 generations shown in this plot. They're denoted by the vertical curved arrows. They're labeled at the bottom by the type of mediation that they represent. And at the top is examples of how they manifest in that particular, in those particular interactions. So cultural mediation, symbolic mediation, which we had for millennia almost. Communication mediation, which of course came in more in the electronic, but also in the analog age. Network mediation, and then the era that we would perhaps argue we're in now, which is one mediated by cyber infrastructure, large computational infrastructures. And again, on the top, you can see the manifestations. And so there's a couple of things to note about this. 5 generations. Now, unlike most generational plots, the previous generations would not be used anymore. But today, we really have up to 5 different generations or types of mediation going on in learning settings, in research settings, in collaboration settings. And you can just tell by how they manifest up in the top that they are not very well integrated at all, and maybe not at all. And there's probably even boundaries between them. So that's the first thing. The second thing is there's a horizontal arrow running through these generations, and it's labeled as increasing complexity of this mediation. And I've never heard anyone dispute that, and it's true. The more and more complex. And of course, I would say that we're hearing about a 6th generation that's already manifest. It's the era of smart data agents. I haven't named it deliberately because that's not my job to name those things. But smart data agents, cognitive computing, and cognitive collaboration, and cognitive classrooms, and you just can sort of see what's happening. So we're faced with a little bit of a challenge because there's challenges in research settings, it's in collaboration, but what about when we think about how this applies to educating the data scientists and data analytics professionals and researchers of the future in the face of this increasing complexity? So I just want you to put that in the back of your mind, and I'm going to come back to it a little bit later. The next diagram, many of you have seen a version of this diagram, which is the what I term, and some of my colleagues term, the data information knowledge ecosystem. It is not a linear progression from data to information and knowledge. That is wrong. If you have any of those charts in your view graph, you should throw them away, because the red arrows indicate this flux between what one of us might think of as information or knowledge and what another might think of as data. And I spent a lot of time in the classes explaining this, but the reason I'm going to use it today is to indicate how I think about this from a curriculum. So I've unpacked this space of data, information, and knowledge, and the ellipses here indicate 3 courses that I created. The Semantic eScience I co-created with Deborah McGuinness, and I teach these every other semester. So data science is aligned on the more data side of things. Informatics, the people in the loop part, which I'm not going to talk about at all really, and the semantic eScience, that's the knowledge representation. But these are all interlinked and they're part of a curriculum, and they have to be part of a curriculum because you can't just teach data and data methods by themselves. And then once you get that core curriculum, we at RPI in the constellation that I'm in fundamentally think the internet is our primary computer and the web is a manifestation of that. So web science underlies all of that. And then we can overlay it with data analytics, or I teach geographic information systems for science. And so we've really built out, and all these courses we've created. And so I'm just going to run through now an example of a program that I direct as a way to indicate what we've been doing and how it's structured. That program is an institute-wide interdisciplinary education program, so it's not a department, it's not in a school. It was developed in the 90s at RPI. It was the first of its kind in the US, and the web science aspect was added back in 2009. There's a link to the website up there. And this is an example of the undergraduate bachelor's degree. There is a core, and you'll just have a look at some of the topics in the core there. Web science, web systems development, web science systems development, data structures, social, cultural, political, HCI, managing the resources, project-based, capstone, and interaction. And the way in which we are able to deliver this very robust undergraduate degree with specializations is through concentrations. We don't have to go to the state and get a new version of this degree approved. I can create a concentration on the fly. We have over 22 of them. And so there are concentrations in engineering, in science, management, and humanities. And you'll see the relatively new one in cognitive computing listed under humanities, because our cognitive science department is in that school. So that's that. Growing out of that undergraduate degree, there is also a graduate degree. So I've just sort of reproduced on the left the Bachelor of Science in Information Technology and Web Science, 20 concentrations. And it has a strong science and humanities core. It has 8 concentration courses, a number of free electives, and culminating experiences, and very project and team-oriented. For the gentleman who asked the question this morning, I don't know if he's here, about graduate programs, we have a Master's of Science in Information Technology. There are over 10 concentrations in that degree. Data Science and Analytics is one, Web Science, and I always have to put this up, Information Dominance is a program that we deliver for the United States Navy N2 and 6 Cyber group. And we have a cohort of students in that right now. The 30-credit degree program has 5 core, 3 concentration, and you can imagine now, to see the flexibility in this program, a 3-course concentration is the basis of a certificate. And on the undergraduate side, the 8 courses is a basis for a minor, and our minors are very, very popular, and as are the concentration courses. Now, here's the kicker. The kicker is that this master's program is both a full-time residential program and a part-time blended program. So it's available for working professionals, and we currently have a cohort in there, and it's all taught with the standard full-time curriculum. Just an example of how we sort of speak about data science and analytics. It's all I don't need to read it to you. You all know what it is. But it's really that this is not so much being concerned with individual types of analyses, but an entire methodological approach, which gives our graduates a basis for adding on the new algorithmic techniques, adding on the new applications and technical approaches as they come along, because they've got a methodological basis, as Yuri said, the research methodological basis. And it has some sort of standard components in there. Now, Drew Conway is not here, right? I haven't seen him. So I always have a little bit of a go at Drew, because many of you will see, Yuri showed some Venn diagrams. We all love I've shown Venn diagrams, we all like them. But data science really is well described by Venn diagrams. So this one is due to Drew Conway. I would say it's overused, simply because all Venn diagrams really are overused. But what I want to do briefly is just introduce this idea of anatomy. So we all remember anatomy, right? Anatomy is the functioning of individual components in your body. And physiology is the assembly of all those anatomical components into a full working body, the body as a whole. And this is going to become fairly important because what I would argue is that in this diagram there are anatomical or either competencies or skills or experiences that have to be embedded individually in a student or anyone who's taking these courses. Now, so they need to know things about machine learning, they need to know about statistics, they need to have substantive expertise in a discipline area. But you'll see there's a few that are not covered. And I would argue really that the assembly as a whole, and certainly data science, has to have a physiological conceptual approach. And that is, they have to have the experience of doing these things all working together. Now, if you're in a graduate program, that's pretty hard to achieve in like a semester and a half. You just don't have enough time. An undergraduate program, you do have enough time to do that. And what this means is, and it's a challenge for educators, is how do we assess the individual versus assessing a group when groups are absolutely essential. So physiology, it means a group. Complementary skills to really tackle aggressive problems and make mistakes and be evaluated on the methodological aspect and the process component rather than just, oh, I got the right answer. Because as we heard a lot today, we don't even know if we got the right answer. And I would also say that Drew's highlighting of the danger zone, the intersection between hacking skills and substantive expertise, which today is really easy to come by because you can download those application packages, you can get those data sets, and you can do things like big companies do, which I won't name here because there might be someone in the room from that company, and just make false claims about results that actually are not statistically valid. So I would argue that there's probably missing anatomy. If someone's getting into that zone, then there's a body part that they're missing that they need to have and currently are not getting it. So what we did in introducing data science then, as I deliberately unpacking the data, information and knowledge into different courses, and then using the anatomy and physiology as a model for what has to be done individually and what has to be done as a group. So just as an example, and this is not complete, but you'll see a lot of the things that Yuri talked about in terms of competencies and skills, data lifecycle, data management, all forms of analysis, and you have to have technical tools and standards. And this has initially been offered at the upper undergraduate level and the graduate level since now 8 years, since 2009. At the physiological level, definition of science hypothesis, guiding questions, brainstorming, critiquing, critical thinking, finding and integrating data sets, presenting them, and presenting the conclusions. So we were looking at this and we said, all right, and this is now about 3 or 4 years ago, we started thinking, all right, we've got this, it's a robust program, but we're pushing out a fair number of graduates, but it's not widespread, and it was very clear that there was a strong desire. So about 3 years ago, 3.5, 4 years ago, Kristen Bennett is a colleague of mine at RPI. She's also Associate Director of an activity and institute-wide centre institute-wide institute, called IDEA, Institute for Data Exploration and Applications, idea.rpi.edu. And she wrote a proposal to the National Science Foundation and funded a project called Datum. It's Data for the Undergraduate Mathematics Curriculum. And as she was writing that, what really became clear, and as they implemented that, what they had proposed, which was an introduction to data mathematics, and then specific discipline-based data-intensive courses in other departments. This was in science, but it's now spread to engineering. And the whole point here was to get data out into the other degree programs. But along the way, she came up with a cool term, and I haven't heard it today, so you've heard it here first, data dexterity. So dexterity, that's something you have to instill in someone in a deliberate way so that they have a level of expertise that distinguishes them from other graduates. And I think this is a really important thing. And because of the way RPI is structured, it quickly and easily became an institute-wide activity. So it's, if you like, data across the curriculum. So data awareness in the curriculum for all undergraduates. Data-intensive course requirements, I'll show you some more details about this. Addition of concentration, certificates and minors to many of the majors, and we have a lot of majors. And then the building out of interdisciplinary courses and programs. And this is where you'll sort of see the first infiltration of the cognitive element in here. But also digital ethnography, analytics masters, campus participation. So really pushing this out as part of our core that we deliver to our undergraduates. And then with the help of some corporations, an insight lab, what's called the Insight Lab, interdisciplinary challenge intelligent technology exploration lab was developed as part of that physiological complement to the anatomy that we were giving them. And then being considerably more deliberate about the data-related cooperative and internship opportunities that had previously been part of sort of now is fairly standard for a lot of universities, but these were now very targeted. All right, so about 2 years ago, our Institute Faculty Senate undertook a review of our core curriculum, looking at what do we do to need to keep it fresh. They were influenced by Kristen's activities and emerging very successful evaluations. And that, I should say, just to finish up, that 3-year program is just coming to its end. It has a full external evaluator and assessments, and it's rated off the charts. So with that in mind, they said, let's have a look, and they proposed a set of changes. They proposed them in 2015, and of course, we're all just getting around to taking a look at them. And the 3 elements here are a common core in another Venn diagram, the disciplinary courses, and then co-curricular activities. And it's a big, long document. I'm just going to pull out the data-related piece of these so you see what the entire faculty is thinking. And the nice thing is, what they're proposing are things we've already got. What we don't have is some of the disciplinary courses. So in the science core, we are adding a data-intensive course requirement. And we've had a communication-intensive course requirement for quite some time. This data-intensive requirement would be in 2 parts. It would be a pre-qualified data-intensive course. So a student can't just take any random course that might have the word data in it. It has to be approved by an institute committee. And then the second part would be a data-intensive course as part of their disciplinary requirements. And those could be projects, they could be bioinformatics courses or whatever. So that's in the science core. In the disciplinary core, then is the data-intensive course sequence. And they're not courses necessarily about data analytics, they're not the generic courses, but they are ones where the instructors, the faculty, have been very deliberate about bringing real data into the course curriculum. And then finally and here's an example. There's just pulled some pictures got these from Kristen this morning. This is an example of our last summer's Insight Lab, and this is being conducted in what's called the beta classroom, which is one of these cyber learning environments with multimedia and cameras and recording and image analysis of student facial reactions and all sorts of things, where we had a series of projects, and it included 20 sophomores and junior math majors, just really as a pilot to try it out and see what it might look like to take it to scale. And they produced some fantastic things, you know, and when they're giving their presentations, they come out with words like, that predictive analytics really deepened the story. And that's what you want to hear from a sophomore, all right? That appreciation, that articulation that, A, there was a story there, and that you can go deeper with these techniques rather than this, you know, sometimes fairly cursory approach to data analysis. And I won't explain exactly what it is, but you get the idea. Next fall, we're setting up a new Insight Lab in one of our buildings, completely state-of-the-art, lots of monitors all over the wall, and it's going to be in regular use for a lot of classes, not just a single lab experience. And then the co-curricular, extracurricular activities, the part in red here, is where the opportunities for data internships, analytics internships, and the really nice thing about that's happening also at RPI is that these won't only need to be during summer. We're going to have a summer on campus for our rising juniors, and then they can go away in the fall or the spring, both on internships but also on cooperative arrangements, with strong encouragement for international experience, strong encouragement for community, for community engagement, and especially in industry, which we've had for a very long time, but it's been more focused on our engineering degree students, but now the data-intensive students are going to be encouraged. So, if you were to ask me what a Rensselaer graduate would look like after going through this data-intensive activity and data across the curriculum. Now, a quick survey. Does anyone here not know who that is? Yes. So when I teach data science, I have 63 students in my data science class this semester. 3 of them knew who this was. I'm going to stop asking because it made me feel so old, but there's a really great story that goes with data, Lieutenant Commander Data. And so if you ever get the opportunity, go back and watch one of the opening scenes of the first episode of Star Trek: The Next Generation, when Data was first appeared. And so Data was on TV, the first data scientist that we really knew anything about. And think through what Data did in Star Trek. And I think it does actually characterize this idea of anatomy and physiology. Data didn't work by himself. He wasn't autonomous. He was working with others. He was always getting new data in. So what we're really talking about are these kids, and they really are some outstanding people. All of our courses are sort of publicly available. They're all on the web. The lectures are increasingly, the lectures will be recorded and might be released. We are a private university, so you can come and talk to me about that. All right, just to sort of bring us home here, I gave a talk at the National Academy a couple of years ago, and they asked me to put together a call to action, and it was fairly detailed. I took a lot of it out, but these are just to sort of give you the spirit. So for data science across the curriculum, I was saying it 2 years ago, our university is behind it and is already implementing it. And the way I phrased it, and I often get a little bit of pushback, is it should be the same as calculus. And RPI is a very strong STEM school, so calculus is not just mandatory, but advanced calculus is as well. But the big thing that we're lacking is this intro to statistics. I mean, I think universities just have completely dropped the ball. And I think it's going to be a really big gap that we need to, so that's one call to action, is to rethink that. I also make the argument that data management, and so so glad, you know, Yuri brought this up. We didn't plan this, but data management is not taught. It's not necessarily intuitive, but it must be second nature. It shouldn't be laborious, but that means that you have to know some of these functional things, these anatomical things, and it has to become routine. You just have to just do it automatically, just like you know how to run an instrument. And then as a whole, this realization, and students need to be educated in this, that data science is a collaborative role, and that one that has to have all these additional skills and competencies to be respected and rewarded by peers and organizations. So that's for data science. For analytics then, to make this really possible in universities, institutions have to step up and provide infrastructure. You know, they've all been supplying network infrastructure now for ages, but they do not supply robust data infrastructure. And it's very difficult for the regular faculty member to go put up a cluster and a virtual machine and a Hadoop server and all this. But it should be there. It should be a facility that is made available by the institution if they've made that commitment to data. Provision of intermediate statistics, and also universities have to put up well-curated and even not so well-curated data sets which students can hone their skills on. But ultimately, this more exploratory, letting students come up and find their own data and define their own problems is really, really at the heart of what we need to do. And that this part of the scientific method that was also to be mentioned a few times, the continuous questioning and critical thinking and doubting and tracing and verifying is really essential. And that has to be, this for data analytics, has to be part of the learning assessments and the outcomes and the critical things that we need to assess from our students. So, well, what's happened then is we introduced data at the upper undergraduate and graduate level, and then through a series of activities have filtered it down. So it's in the mud. That's where the sediment is, right? It's made its way down into just the lower levels of what's going to be part of every RPI student's experience beginning in the fall, next fall. So let's just come back briefly, since this is a world of Watson and cognitive computing. And I showed you this chart at the beginning. Cognition plays a very important role in data science and analytics. It plays a huge role in informatics, which I decided not to try and talk about. So we need some evolution of cognitive systems where there are very many humans in the loop. And this is one plea I make. We cannot afford to push humans out of the data science or the data analytics loop. There's an obsession with machine learning and other automated outputs and turnkey systems, but we have to put humans back in the loop. That's the best combination. And this has an implication for how we think about teaching cognitive computing. And so basically we're just about to start pushing the cognitive computing back down in the curriculum from the graduate. It's already been at the graduate, at the upper undergraduate level, and down to the introductory level. Even though we have a concentration in cognitive computing, I'm not very happy with it. It's not robust, as only a small number of students take it. I would say that ultimately we might see cognitive computing across the curriculum appear, and it might be in combination with our humanities core requirements, most likely, but I don't know what it looks like yet. But that's sort of my prediction for what you might see from RPI. And that's all I had.
Yeah, that was really good. So one thing, I'll just do a quick advertisement for those people that are sticking around for the week. Some of you are only here really for, there's a lot of echo there, for today. Is Shannon Valor, who recently wrote a book on ethics and data, right? Technology and the virtues. She's speaking here, I think, on Wednesday. So if you go into the tool and search for Valor, V-A-L-L-O-R, go hear her talk, because I think that's a fundamental piece of this future thought about thinking about the ethics around all the things that we're doing, and how does that end up applying to public policy and bigger issues. we're not teaching people, I mean, he had data ethics up there and didn't really talk to it, but we're really not teaching the average student ethics in a constructive way to help guide stuff. Right? Historically, we've kind of left that to churches or something, or to a random class that some students take but most don't. Right? So how do we make it part of the core curriculum that people are taught a construct to think about ethical problems to guide our future in the world of cognitive? All right, so I'm going to open
Steve,
it up to questions.
let me turn that into a question. So we have a graduate course on big data policy and ethics right now, and the undergraduates are desperate to get into it. They've already seen that writing is on the wall.
Awesome, that's great. All right, so we have plenty of time for questions, but I still want to cut it short a little bit just because we're going to go back to reconvening the room, configuring the rooms. So we're going to bring both groups back together for the panel at 6. So if you got questions, raise your hand and I'll bring the mic to you. All right, Yuri.
Peter, you are really looking deep into education and putting this in the cross-university, cross-subject and specialities. But do you think that we need to go deeper in the school education? And there are projects that actually Oxford in UK that if I remember, that they try to teach statistics from the school level, or maybe from even first forms. Do you think this needed?
Yeah, so we do, absolutely. I'm always a little bit reluctant to tell other people what they should do, especially at levels of education that I'm not directly involved in, and I don't sit on any advisory panels. But so about 15 years ago in previous position, we undertook a what's called the non-expert use case. And the non-expert use case was getting authentic data into high school classes. Yeah. And we found the huge barrier. The huge barrier was the teachers, A, didn't have the time to get that data ready. They couldn't find it. They couldn't determine if the images that they were finding were representative of the data. And so there's really a big gap there. And the new education standards have just come out, at least in the US. And I believe that there's a new requirement for statistics in there, but it's going to take some time for that to come through. But what's really needed, because I don't know how old your students are, but even though when I ask them, have you done statistics? Yep, they raise their hand. And as soon as I ask them what a binomial distribution looks like, I can't even guess. And they don't even understand that a parametric distribution has parameters in it. And so it's the gap between when they might get it and when they're going to now step up and do a really challenging. So I spend a week and a half in data analytics just giving a refresher course into, parametric and non-parametric statistics and a little bit of probability for Bayesian and
yeah, and it usually gets into that the core fundamentals have to be revisited.
Yeah.
Right? It's stats for every student. It's probably linear algebra for anybody that wants to become a data scientist. It's teaching students to be scientists.
Yeah.
Right?
And
it's not normally taught.
No, it's not. And if they were taught it and they remember it, they tend to remember the central limit theorem, which is confounded by a lot of big data that are fundamentally high variance. And I have a lot of trouble getting through to them that high variance really does mean something. That means it's actually representing something real going on. Yeah.
All right. Any more questions? All right. Richard's back here.
Thanks, Peter. Thanks for that. It was a great discussion or talk to us. I don't know much about Rensselaer, but are all your students sort of in STEM, or are they across the entire discipline of sort of literature and such like?
Okay.
Because that's rather important for what I'm trying to do.
It is, yes. So I normally put up the demographics. We have 5 schools: architecture, Lally School of Management, Business Entrepreneurship, Humanities, Arts and Social Sciences, which is cognitive science, arts, communication and media, science and technology studies and economics. No history department, unfortunately. No explicit history, that's in STS. And we have engineering, sort of your typical engineering school. RPI is highly rated science. We have astronomy, astrophysics and applied physics, biology, chemistry, computer science, mathematical sciences, earth and environmental science. I think that's it, 6, yeah. We're about 60% engineering, 55, then 25% science, and then the other 3 are split. So highly leaning towards a sort of science and engineering school. But so RPI is the oldest technological university in the English-speaking world. So even our artists are tech savvy. You know, the poets are tech savvy. They've already got that inclination.
Thank you. Anyone else? All right. Unless there was a hand up over there.
So the question, I'll repeat the question. As far as programming, A, what are the programming requirements, and B, are they required? Interestingly enough, we don't require any programming language as a prerequisite. In fact, computer science recently discontinued its offering of its Java course and its Python course. Instead, what we're doing is we're putting all of the programming requirements in the courses that use them. So Intro to CS uses Python. Data structures introduces them to C++. Data analytics, I use R and Python, and RStudio and Jupyter Notebooks and all of those things. But I teach that in the lab alongside the problems that they're doing. And it's a little bumpy for the start. The undergrads just eat it up. They just love it. Grad students who've been set in their ways a little bit longer really don't like R. They'd be much more comfortable with MATLAB. But I basically encourage them to use any programming language they want. There's no requirement that the assignments are done in R, but I teach R as part of the class. And I give them code fragments and things like that. Relatively few of them code anything in a compiled language anymore for these classes. Very few use C or C++ or Java. They're all using scripting languages.